Chapter 2, Digital Electronic Signals and Switches. Digital signals. The basic timing diagram associated with digital signals is a voltage versus time diagram. This shows the logic state. As you can see in figure 2-1, you have 0 volts is 0 logic level for digital, and 5 volts, analog 5 volts, is digital level 1. And the interpretation is not exactly 0 or 5 volts. It could be 0.1 volts or 4.97 volts as an example. We use the oscilloscope to view these values. The clock waveform timing is a periodic clock waveform. It's repetitive in form. Most digital signals require precise timing. Special clock and timing circuits are used to produce waveform clocks to trigger the digital signals at precise intervals. We have the period of your clock waveform and the frequency. You can calculate the frequency by using the first formula, F equals 1 over Tp, which is the period, and period, which equals 1 over the frequency. Some engineering notation to note for this chapter, as well as the rest of this textbook, is the common engineering prefixes giga, mega, kilo, milli, micro, nano, and pico. These have the abbreviations, but more importantly, the powers of 10. We have milli, micro, nano, and pico, which are all to the negative powers of 10, 3, 6, 9, and 12, and kilo, mega, and giga are to the positive powers 3, 6, and 9 as shown. The ones that you'll be most concerned about will be kilo, milli, and micro, as they are most commonly used with resistance, voltage, and current. There's a serial representation of these values. We put them in through, say, a computer. You'll be able to find that is either serial representation or you have your parallel representation. Serial representation is usually slower and requires 1 bit for each clock period. Some examples of serial would be your COM ports and your USB. Parallel representation, on the other hand, is very expensive, but it's also very fast. Mostly used in the computer world. A separate electrical conductor is required for each bit, however. Some examples of the parallel representation is the LPT1 and the SCSI. LPT is your printer port, and BPS stands for bytes per second. There's some switches in electronic circuits. These make and break a connection like an on or an off, like a simple switch, like your light switch in your room. The manual switch of electromechanical relay is also a type, and the semiconductor types, diodes, and transistor switches. Manual switches and ideal resistances, on is 0 ohms and off is infinite ohms. There, you think of your light switch. On, the circuit's on, your light is on. Off, circuit has a break in it, so the light doesn't turn on. A relay is a switch. It's an electromechanical relay. Has contacts on either end. When it's on, contacts are connected, and when it's off, they're not, and requires an external voltage to operate. Say you have a motor you wish to operate and you have a relay as a switch, you'll have a microprocessor taking that value from your microprocessor, turning it into an on or an off signal, which turns on your motor. You have 2 types of relays. You have your normally closed and normally open. This determines whether or not you want, when you have your on voltage, you want the motor to be on or off correspondingly. Some disadvantages to having a relay is that it takes a lot of current to operate. It's also slower, takes several microseconds versus, say, the micro or nano unit for time. And it's an energized relay coil. These can damage easily, and you can replace the source with a clock oscillator. This is a timing diagram for that relay. You have your clock pulse 5 to 0 volts and your output of 5 to 0 volts. This basically determines you have your 5 volts, meaning the coil is energized and the contacts are closed, meaning you have your output is off, meaning you have a normally closed relay. This is because 0 volts is displayed for the out when there's a 5 volt clock pulse, and so on and so forth, along with the other side of it. With the 0 volt clock pulse, you have a 5 volt output. Another type of switch is the diode switch. This is a semiconductor type of switch. The current flow in one direction only. There's two types. There's forward bias and there's reverse bias. Forward bias, you have the anode is a more positive terminal than the cathode, and current is allowed to flow through this type. However, the reverse bias, there's no current flow. The anode equal or more negative than the cathode in the reverse bias type. You also have 0.7 voltage drop across its terminals. This is constant for all silicone diodes. Here's a graph of that 0.7 drop showing you have the V reverse and V forward, and your currents as well, showing that it's not exactly 0.7 volts based on your current, but it's pretty close. This is due to the ideal world versus real world scenario. The next type of switch is the transistor switch. It's a bipolar transistor. You have your two types, your NPN and your PNP. The N stands for negative terminal and your P stands for positive terminal, or junction as the book describes. The NPN type is a positive voltage from base to emitter, and the collector to emitter junction is a short. As you remember, a transistor has 3 pins: collector, emitter, and base. And an NPN also, negative voltage or 0 volts from base to emitter, and collector to emitter junction is open, meaning transistor is off. The PNP, on the other hand, is the opposite, with a negative voltage base to emitter, meaning the transistor is on, and the positive voltage or 0 volts from base to emitter is off. Second to last is the TTL Integrated Circuit. It's a transistor logic. An example of this is your simple 7404 inverter. This takes a digital level input and complements it to the output. The inverter more specifically takes the input and reverses it. Say you have a 5 volt or digital level 1 input, it'll convert it to a 0 volt 0 output. The 7404 is a hex inverter in chip form, IC form. It's 6 complete logic circuits. It's a single silicon chip, 14 pins, and 7 on each side. You also have your DIP package, this is shown here, with your 14 pins, your 6 inverters, and you've got your pin 14 as your voltage source for 5 volts, and your ground is pin 7. And you have the CMOS integrated circuit types. These are mostly used in industry. They are low power consumption devices and battery powered devices. For educational purposes, however, you will mostly use your TTL style chips. These have it's a faster switching speed, and it takes a little more power. However, to understand the concepts and to see your values change on your oscilloscopes, these are much easier to determine. You also have surface mounted devices. These are no smaller than maybe a dime. You have they're also way less and a lower cost. They can be soldered directly to your PCB board, your printed circuit board, and they operate at higher frequencies, making these types of packages much more compatible to the industry world that we know of today. So in summary of Chapter 2, the digital level for 1 is commonly represented by a voltage of 5 volts in digital systems. A voltage of 0 volts is used for the zero level. This will be ingrained into your brain for the next year. You will understand that what an oscilloscope does and how it is used for these digital and analog signals. The frequency of a clock waveform is equal to the reciprocal of the waveform speed. You will understand this further when we get into things like counters and shift registers, which are dependent on the clock waveform. And also, this chapter demonstrates the transmission of binary data in the serial format requires only a single conductor with a ground reference. The parallel format requires several conductors but is much faster than the serial form. We also have our relays that we went over, forming opens and shorts in circuits, requiring higher current values but not high speed. Diodes are used in digital circuitry whenever there is a requirement for current to flow in one direction but not the other. Granted, you have your 0.7 volts voltage drop across the diode if it's silicone. The transistor is a basic building block for the modern digital integrated circuit. It can be switched on or off by applying the appropriate voltage at its base connection. You have your two types of integrated circuits, your TTL and CMOS integrated circuits. They are formed by integrating thousands of transistors in a single package. They are the most popular ICs used in digital circuitry today. And lastly, you have your SMD, your surface mount devices. These are gaining popularity over the through-hole style DIPs ICs because they're smaller in size and reduce manufacturing costs. This is just the basic for the later chapters, which we will discuss more in depth of how the clock signals, the transistors, and all types of the package devices are used in our industry.